Okay, so that's enough tap dancing. I think we're back on time now. I think we're going to do this.
Most AI researchers work with data. Sulimon Sattari works with the data your body makes when it's fighting for its life. Physicist, nonlinear dynamicist, ICU analytics, medical waveforms, time series analysis in intensive care environments. He brings the mathematics of chaos theory to the most human problem of all, keeping people alive. And at Kwaai, he's making sure the AI of tomorrow is built with that same rigor and care. Ladies and gentlemen, Sulimon Sattari.
Hi everyone. I'm Sulimon Sattari. I am moonlighting as Director of Research for Kwaai. Today I'm going to be talking about research at Kwaai, and I'm going to be talking about specifically a problem for decentralization, which is encrypting your data before you send it out, and how we can allow LLMs to do computations on data without ever actually knowing the raw data, only knowing the encrypted data. First overview of Kwaai. We have a lot of different research areas open to new ones, all within the ideas of safer, faster, greener AI. I'm going to be talking about the homomorphic encryption. Riza touched on the graph rag, and we also Ben spoke a bit about fluidic neural networks, things that we want to explore more. Always looking for new people that are interested in these problems, talk about them, target conferences or journals, things like that. And so I'll be talking about specifically homomorphic encryption. So quickly, what is RAG? RAG is how you can retrieve the most important parts of your document. As we talked about, when the LLM does inference, every single token is adding a lot more computation, is adding a lot more heaviness to everything. So you don't want to feed the LLM, just even not from a security standpoint, but from a computational standpoint, you don't want to feed it your whole database. It's going to cost a lot more. So first is a RAG step, which is take all your data. Let's say it's all your transactions, your medical data, whichever data it is that you're applying LLMs to, and chunk it into portions. And then once you've decided on your chunking, then every vector, every chunk is converted into a vector, like a 1000 three-dimensional or whatever dimensional embedding you're using. Every document is converted into a vector, and then that's your vector database. And then when you have a new query, like what was my my medical bill on November 17th, then you take the embedding vectors that you created, and then your user query gets also converted to a vector, and there's an algorithm to get the top K vectors, and then you might feed the result to an LLM to ask it to tell you something about that. And so we're talking about trust today, and this is the trust barrier that you might want to put. So can I encrypt everything? Can I only send data that's not my data and still have the LLM or the RAG system give me back? And the answer is yes. That's what I'm talking about, how we do that. So in confidential RAG setup, let's say Bob is your trusted partner, your accountant, your doctor, somebody that you trust, that you share your data with. We all people that we share our data with, and Bob is going to help you with your queries on this data. And so you or Alice, you want to query the data, your data, which Bob has. You trust Bob, but whatever computational source Bob uses to make inference on this data, you don't necessarily trust. And so that's and even if you do trust that source, you might not trust downstream sources or other sources that can try to hack at that data. And again, that's the trust barrier that we're drawing. And so, as always with research, we stand on the shoulders of previous giants that have thought about this for a long time. In the 70s, the same Rivest who invented RSA encryption, also with his colleagues, wrote a paper on how we can think of a computer system, and an example for them was like, I want to calculate profit without feeding all my transactions to the computer. So how can we do that? well, I have my smaller computer that's in my physical secure location, and maybe we can encode the data before we send it out and send some scrambled data, which then by algorithm means that some scrambling that preserves what the profit calculation would be. And so they came up with a pretty they came up with an algorithm that works for this, but it doesn't work necessarily for every calculation. And so they proposed homomorphic encryption, encrypt the data before you send it out, do the calculations on encrypted data alone, and hope or use a protocol that preserves the final answer. And Craig Gentry also in 2009 solved fully homomorphic encryption, which means you can take the data, completely encrypt it, and do any calculation that can be done on logic gates on that encrypted data and still get the same real unencrypted result. But it's not computationally feasible, that method. So this is a big area of research, people still working on it, including us, to find new methods of homomorphic encryption and apply them to different areas. So let me formalize a little bit more how this works. So you take raw query vector, you're able to convert your question into a vector on your own machine. That's not too hard to do. And or you send your raw query to Bob, and then Bob encodes it into a scrambled vector. We call that QS. And the scrambled query and all of your scrambled data goes to Eve. And for example, for the dot product, we can think of a way, which is usually how RAG is done, is by taking the dot product of these data vectors. And we know that if you scramble the locations of all the vectors, of the elements of the vector, it still gives you the same dot product. So I can give him a completely scrambled vector to the computational source, and it will still obtain the same dot product. It'll still give me the same indices of what's the most relevant document, and that, therefore you can do the whole RAG without ever sharing the original documents with the computational source. Yeah. And so at Kwaai, we thought about this problem, and we also went out to Society of Industrial and Applied Mathematics and applied for the workshop that they have, mathematical problems in industry. So we got around 15 masters, PhD, some professors, some students, to all sit in a room for 5 days and think about this problem, specifically applying homomorphic encryption to RAG. How good is our algorithm that we described with scrambling? Can that be hacked? And worked it out. And we had an anonymous donor donate $10,000 so we can work in the workshop. And we had a lot of fun, Riza and I, going out there and whiteboarding solutions and exploring different things. So the final kind of result of this, we came up with kind of a trifecta of what. So first we came up with a list of algorithms, and then we came up with a trifecta of how we compare them. You have computational cost. How well do they encrypt? How hard is it to hack your encryption? And how well does it preserve the same result? Some of them are not perfectly homomorphic. Only they have some error term in the result. And so we identified kind of these three. And like in engineering or in many fields, it's like you have to pick two. So it's hard to get all three of these, as we found with the algorithms that are out there. And so we identified. So we had 3 algorithms we came up with, and there were several that we found in the literature. I listed kind of the one that's the best. And so computational cost-wise, the one that was the best obviously was the most expensive. What we came up with is considerably cheaper, and we'll see that, as far as preserving the true answer, some of the algorithms didn't perform so well on that, and others did. One here means the encrypted result is exactly the same as the unencrypted result in all cases, and then these lower numbers mean you got a different result. And then lastly, there's encryption effectiveness. So how hard is it to hack these algorithms? And so CKKS being one of the hardest to hack, but also one of the most expensive to apply. So yeah, actually, Myra's going to talk about this, so I won't mention too much. But we have an intern group as well working on RAG and benchmarking different vector databases. We're planning to actually use this in Kwaai-net, which Riza has talked about, Kwaai-net being the distributed LLM inference. So can we include this? I mean, that's the end goal, is including homomorphic encryption, so that if you're part of this network, you're not taking data from all these, from everyone that's involved. And so, yeah, join us if you're interested in research. Contact Reza. I put my contact information here too if you want to talk to me about anything I've talked about. We have different projects, and this year I really want to target NeurIPS, see what we can gather from the research that we've done at Kwaai and collaborators that want to talk with us, and try to publish something in one of the conferences, or maybe do another SIAM workshop on another industry problem, and continue the producing new knowledge that's going to help our cause. Thank you.
Thanks so much.
Okay.
We got some questions over here, just behind you, Ted.
Yeah, I've been reading about RAG with the re-ranking that will bring the relevance document back to the context query. Have you experimented with that re-ranking process?
No, I haven't.
Okay.
I'll look into that.
Any other questions?
Has anyone heard about homomorphic encryption before this? Okay, so a few people have. Today, without homomorphic encryption, you are having to trust Sam Altman, or even Dario. You might like Dario. You look at Dario, you think, he's like sort of the punch the monkey. You feel like he's that monkey. But in any case, you have to trust them. And when you want to use their AI services, you have to upload your context in clear text. Is there a way in which you can upload it securely, so they can still run AI on your content, but they never see the raw content, and you get back the correct answer? And we've cracked that within Kwaai. Question.
Is there code that we can see about? Yes.
There's a paper.
Yeah, so on the Kwaai GitHub, I think we have the code, and you can reach out to me. I'll update the GitHub if it's not in there already. Yeah. RAG is retrieval augmented generation, meaning when I send data to LLM to infer, I don't want to send the entire document. I want to retrieve the parts of the document first. It's the retrieval step. What part of this textbook has the answer to the question I want? Most likely.
In user terms, if you were to ask ChatGPT, what's the capital of France? Okay. It'll know that because it has general knowledge. If you were to ask it, what's the eye color of my grandmother? It would not know that. And so you augment the LLM with a private data set. And that's what is called the context sometimes, that you upload to your favorite AI system. And then the LLM just does what's called the chat completion. So you first do a retrieval of your knowledge base of, give me the top 10 chunks of my knowledge base that could form the answer, and then the LLM just does the simple job of taking that data and structuring it into an answer. So you're not relying on its general knowledge, because it didn't know who your grandmother was. Okay, so I hope that's answers the question about what's RAG. We've got a question over here.
Yeah, so in regards to RAG and data, there's a lot of experts who they have expertise and knowledge, so you could build them their digital twin. How can they trademark that?
Yep, exactly. I mean, some of the speakers were alluding to that, about individuals having their own, creating an economy of knowledge rather than the tacit assumption that the half a dozen oligarchs who control AI have, is that all the data they can see is theirs to grab. Instead, we believe you own your own data and you get to choose how to monetize it. But you might also want to choose your private collection of experts that you want to draw upon. And so what Ben was talking about earlier on was about a distributed graph knowledge base, where it's not just your knowledge, but you get to pick the 200-300 experts, and when you do the query, it's drawing from their knowledge. And not necessarily free, that might be a paid service. But it allows each of us to construct our own expert council, for instance, from a distributed knowledge base. So I'm talking through your yeah. Carry on. Great. Okay.
This is more of a question for the presenter. The methodology in use for homomorphic encryption, you're preserving the properties of the dot product between the vectors, if I'm understanding correctly?
Yeah, so we examined L2, cosine similarity, and dot product. But
Gotcha.
yeah.
So do you have any concerns with data leakage by virtue of the fact that you're preserving relationships between data that is supposed to be confidential? Many encryption algorithms specifically make self-similar information not appear self-similar to prevent this sort of leakage.
That's a really good point. We definitely need to, I think, look back into that more. So we took the algorithm and found the best known attack method that's in the literature for each algorithm and applied that. But I know that, you know, it's kind of hard to do that for maybe new algorithms that no one has come up with,
I was just wondering if you had seen the result from Cornell, I think earlier this year, about translation between vector spaces, because they found some pretty interesting relationships on like latent spaces that you can construct between vector spaces with enough samples. So if this is really deep into the research, if you've built like an effectively kind of pseudo-random transform, you might actually be able to deconstruct some interesting data.
We did develop a solution to that attack, so we don't actually return to you the vectors that you're querying. We only return the index of the vector, and so you're really operating under two cryptographic regimes. One is the scrambling of the vector, and then when a third party, when Eve, the untrusted host, is hosting your vector database, the vectors are in a random order, and that randomization is a key, is in effect a cryptographic key. And so when you say, give me the top K results, it's not actually giving you the results, it's giving you the index of the results and the similarity score. So it's very difficult to get to figure out what the actual vector was.
Okay, so one last question. I saw somebody with. Okay.
Just to follow up and clarifying the use of this. So a use case might be, say, a developer that has developed a library or a set of libraries and say coding standards over 20 years, and they want to take advantage, they want to hire a general purpose AI, but they don't want to provide their 20 years of research and development to that AI so they can be joined into a general model. And they're willing to pay for that, but they don't want that. In fact, I'm that guy, right? I've been in that situation. I'm like, I'm going to upload this and I'm going to give away my competitive advantage by uploading it. And so therefore I don't want to use it.
That's exactly the kind of use case.
That's exactly the use case, yeah.
Awesome. Yep. Thank you, Sulimon.
Sulimon, thank you so much. Thank you.